Welcome everyone to the post-coffee break session. We have two talks in this session, and the first one is by Kabir Ramola from TIFR Hyderabad, and today he's going to talk about universal stress correlations in crystalline and amorphous packings. So over to you, Kabir.
Thank you. So the work I'm going to describe today is done in collaboration with a PhD student at TIFR Hyderabad, Roshan Maharana, and ex-PhD student Devankur Das, who's now at University of Göttingen, and Pinaki Chaudhary, who is sitting here in the audience. So today's talk is going to be about universal stress correlations in crystalline and amorphous packings. It's a curious result we found while analyzing local stress correlations in many different sorts of long-range, short-range models. We found some surprising universality, which is what I will discuss today. So here's the outline of my talk. We present a universal characterization of stress correlations in athermal systems. I'll describe what I mean by athermal systems. These stress correlations that I'm going to talk about are actually found in energy minimized configurations in particles with soft interactions. So if you were to look at glassy configurations drawn from some parent temperature, you would be looking at the inherent structures. That is what I'm going to be talking about, and that's where the stress correlations are being measured. And then we present these correlations across a wide variety of initial conditions, both in crystalline as well as fully amorphous packings, and in some cases we can derive exact analytic results, and so I try to characterize this universality in different ways across different models, and what we find, this is sort of jumping to the conclusion, large length scale behavior of these correlations seem to be independent of most things, including orientational order, structural correlations, or even the range of interaction, even the type of interaction. This seems to be surprisingly universal. So I'll try to motivate why that happens in the rest of my talk. So before I go into that, I'd sort of give a brief introduction of what kind of materials I'm talking about. So what I'm really doing is measuring such correlations in simplified models, but the kind of materials we are trying to model are these disordered amorphous materials, which are sort of ubiquitous. Here I'm just showing some sort of different kinds of materials that can be described with these simple computer models that I'm representing here. So, cellular epithelial tissues, foams which are sort of robust to thermal fluctuations, rigid particle packings that also display elasticity at the large length scales. Even though the individual particles have some sort of elasticity, the macroscopic elasticity emerging from these disordered networks is quite different. So try to understand such systems. We look at simplified computer models made out of spheres that interact with some short range or long range interactions, which is what I will describe in detail, and these seem to reproduce many characteristics that we are interested in, including amorphous elastic behavior, which I will sort of describe. So just to go through the original formulation of elasticity in a continuum, what you would do is you would write down the static equilibrium conditions. Basically the divergence of the stress tensor is equal to the external force applied at every point in the continuum elastic model, and then you can sort of write down a strain tensor, which is governed or given by this derivative of a displacement field at every point. So you take an elastic object, you deform it because of some external stress, and you have a displacement field from which you can symmetrize and create a strain field, and a strain tensor then can be written in terms of a stress tensor using linear elasticity constants. So this lambda ijkl, which is a 4-index object, is basically an elasticity constant tensor, and because of this linear elasticity, now I have this equation of static equilibrium. I get the closure relation for the strain field. So if I put this equation back in here, I will simply get some second order equation describing the displacement field of elasticity known as the Cauchy-Navier equation, and this is quite general. It tells you that in response to an external force applied on an elastic object, what is the deformation field that will occur through this very simple mapping. You will be able to, if you solve this equation, get the displacement field, and if you have the displacement field through this equation, you will be able to get the stress tensor, and so this basically gives you the stress response of an elastic object. And these constants that you see, mu and lambda, and which are there in this equation, basically represent the bulk moduli and the shear moduli of the system. So those are elastic constants. So this is linear elasticity theory. So the question then naturally arises, what happens if you have a disordered network. So if I look at one of the configurations that I was showing you right at the beginning of the talk, where you have particles which are arranged in a random spatial geometry, then is the same question valid, or is the same theory valid at the length scales that I'm considering here? For example, at the particle scale, clearly this does not have a well-defined original state, which is some crystal or some sort of nice ordered arrangement. So what you would have to do is create these packings and then actually solve the equations of force balance on the disordered network. Each network is individually different, and so then the static equilibrium conditions no longer become these homogeneous equilibrium conditions on a continuum. You would have to actually solve this at the granular scale. So here I'm showing what you'd have to do. So you'd have all these contact forces between particles. So if you take this particle, there's some contact force between this particle, and this particle. For every particle, you'll have to basically sum up the contact forces, and that will sum up to the external force. And similarly, you'll have a torque balance condition, and what you could do is define a particle level force moment tensor, which plays the role of a stress tensor, and this is not readily amenable to continuum treatments, but you could then write down some coarse-grained elasticity theory and try to see how well this can be solved. Okay, so this is the challenge of disordered networks that we want to solve. So just to jump ahead and tell you why it's a difficult problem, if you were to look at what happens to the stress transmission in such granular systems, you see extremely inhomogeneous propagation of stresses. So here's an experiment that is done on photoelastic disks. So you have a two-dimensional structure of photoelastic disks which are sensitive to stress. So if a disk is more stressed, then it scatters more light, and you create these granular piles. So you create a granular pile over here, and they're just two different kinds of disks. One of them is hexagonal disks, one of them is pentagonal disks, and you basically see that depending on what the inherent geometry is, or the underlying geometry is, the propagation of stress, because the weight has to be balanced, the weight of this pile has to be balanced somewhere here, so the stress has to transmit from the top to the bottom, but the way it transmits is highly inhomogeneous and very dependent on the network that forms. So for example, if you were to shake this and let it settle again, it will not form in the same exact point, but there will be very different stress propagation properties depending on the network. But so what can you do? Is it still hopeless? Can you actually write down some continuum elasticity treatments? So what we did was looked at the same problem of stress transmission and created a packing, a granular packing, and created some sort of deformations or local stresses. So for example, here we took this local region of the system and added some forces, so represented with the arrows that are pointing downwards, and we had to balance the forces somewhere, so we created this line and balanced the forces. It's basically like pinching the system, trying to understand what the stress transmission properties of the system are. So as I said, for one configuration, it is highly dependent on the internal structure. But then we asked the question, so here we said, what does the stress tensor, the local stress tensor on every grain, look like before this pinching has happened? So it looks like this, and after the pinching happens, it looks like this. So extremely, after the pinching happens, it looks like this, but it has been averaged over many different configurations. Actually, if you look at the color bars here, this is 10 to the minus 2, this is 10 to the minus 4. So what we do is we look at the change in the stress tensor because of this pinching, when you average over many realizations. So in one realization, you actually see nothing. You basically see random noise. But if you average over many realizations, slowly you start to see an emergent stress tensor that appears because of configurational average. And what we can do is apply the theory of linear elasticity and ask the following question: what would be the stress tensor that linear elasticity predicts in this geometry? So you can basically solve the Cauchy-Navier equations in this geometry, and we get basically the same stress response that you get from a disordered network on average. So the point then becomes that average stress response of a disordered network, or average properties of the disordered network, really resemble the properties of linear elasticity. That is a curious phenomenon that we would like to explore further. Yes, please. No, so these are the, so I haven't added any, let me go back, I haven't added any friction in this. So yeah, this would be a very different object if you added friction, but you can't generate these microscopic models with friction. You have to have history dependent interactions, which, that's a little tougher. So these are local interactions without friction. So what you could do next is sort of create a field theoretic description of such a system, and I won't go into much detail on this, but what you can do is imagine that you have a stress tensor field of the system and posit a partition function description. So what you can do is you can say, given some external forces, there are all possible fluctuations of the stress tensor, the local stress tensor, allowed in the system, consistent with the condition of mechanical equilibrium. So I'm characterizing the full stress tensor landscape, allowing only for mechanical equilibrium configurations. So what that you would impose in some sort of delta function constraint, saying that there is a divergence of the stress tensor is response to an external force, and everything else is just a Gaussian fluctuation of the stress tensor, which is some probability distribution, which is some exponential, which is given by this action. So you can say every component of the stress tensor just has some quadratic Gaussian behavior, and the connecting elements is given by some correlation function matrix, as usual in Gaussian field theories. And you can basically then, just from this very, very simple partition function, try to derive what the correlation functions look like. These equations look complicated only because you have these indices, but actually it's just a Gaussian theory with Gaussian correlations. And if you actually do the calculation and predict what the correlation function looks like, you can actually get the correlation function in Fourier space, and this is recently developed understanding of low temperature physics of constrained spin systems show these very interesting properties called pinch point singularities. I'll describe this in great detail. You can actually compute from this Gaussian theory what the correlations look like. So then the question becomes, can we match this? And indeed we can. So I'll go through this in detail. In 2 dimensions, this lambda tensor, this is a mixing tensor of the Gaussian action for the stress tensor, actually can be written as some diagonal form in this manner. And if you do posit such a diagonal form, you can actually derive the correlation functions. So these are the correlation functions in Fourier space, and angular dependence of the correlation function in Fourier space, which is basically given by the formula I described in the previous slide. One thing to note is that really it only depends on the angle, and this will come into play later. I will show you more evidence for this from microscopic theories. It only depends on the angle, so it depends on how you approach q equal to 0. That is, the large length scale limit gives you different correlation functions. So this is telling me that there's anisotropic correlations at the really large length scales, which I will show evidence for. So this was the field theoretic description. So then we decided, why don't we test these correlation functions in microscopic models where we can actually calculate things exactly. And for the next 10 minutes, I will sort of describe some microscopic models where you can do some exact calculations, and we will then calculate the correlation functions for the stresses, stress distributions in such models, and surprisingly we see that it matches very well at large length scales with this field theoretic description. Yes? Yeah, it's because you have this sort of constraint. This constraint really gives you the anisotropic correlations in this because of the mixing. So if you impose this along with this mixing tensor, you get anisotropic correlations. You can actually go to coordinate independent representations, and you can see that will occur. But yeah, yes please.
So there is no Q dependence. So this is because this field theory is purely local. So it's only exactly the Q0 limit that you can extract.
Exactly. So as you're pointing out, when Q is equal, there's no Q dependence in this action. So that's why there's no Q dependence here. But if you were to add some R prime, R double prime and integrate, you will possibly get some Q dependence at the low speed. But that I have not checked. But that's a very good point. Yeah.
Okay.
Yeah, it's a very good point. This exact theory has no Q dependence because of this. But another point I would like to make is that if you did not impose this, and you just had a Gaussian action, you would get the usual 1 by q squared dependence. That is the liquid-like correlations. Because you have the local constraints, you get this q independence, and that is what the pinch point singularity is. Yeah, so the kind of models that I'm going to describe in the next 5 minutes is basically spring-like models where you have particles that are interacting through spring potentials, or you can have these deformable particles which are slightly deformable, and so you have basically harmonic interactions between particles, or you could have Lennard-Jones particles. So we are Lennard-Jones basically with a cutoff, so up to some radius you have some interaction between particles. So we are going to look at these two models. I'll describe them in more detail in the next few slides. So harmonic interactions are basically particles that have a small interaction through an overlap. This is some idealized model of slightly deformable particles, and this is sort of used a lot in the jamming literature or the granular literature to understand the jamming transition. So where you basically have distance dependent interactions where if Rij, which is the distance between particles, is greater than Aij, which is the summation of the radii of particles, you basically have zero interaction, but if there is a slight overlap, the harmonic interaction turns on. So what you could do is now start with a crystalline configuration and add a little bit of disorder in the radii of particles. So Ai is basically the radius of every particle, and you can add a little bit of disorder at every site using any protocol you would like, but the natural choice would be have a small uniform distribution about 0 and tune the amount of disorder by some polydispersity parameter, which is what we do. Another model that we study, where we can again derive exact results, is that you ask you look at the Lennard-Jones interaction with some smoothness, which you can basically add other terms so that you have smoothing of the potential at this interaction cutoff, and there's again a cutoff distance which is basically 2.5 in this case, up to this interaction radius where you have this circle plotted, and you can again add quenched interactions into this model by labeling the particles with they're either small or large particles, and you can actually add a little bit of quenched disorder and create near crystalline configurations. Again, so these are protocols that are already very well known in the literature, so we are just following that. So once you have this, you can actually create something known as a disordered crystal. You can tune from a crystalline configuration all the way to an amorphous configuration by introducing this quenched disorder. So in this case, this is a short range harmonic interaction. We add the polydispersity to the system, to the particle sizes, and we tune the disorder all the way from crystalline to the amorphous case, and you can actually see that there is contact breaking with increasing disorder in this model, but it still has very high crystalline order up to a large polydispersity. And if you look at real space correlation functions, it's very hard to distinguish between this configuration and this configuration. Here the color represents the number of neighbors of every particle. So there is a nice phase transition that occurs if you look at the polydispersity on the x-axis and you look at the overcompression, so how far you have compressed from a crystalline configuration, and at some amount of polydispersity you go from a crystalline phase to something known as a disordered crystal phase, which I won't discuss in too much detail today, but you go all the way to an amorphous solid by increasing polydispersity. So the question becomes, let me just go back one slide. The question becomes, can we now, because we have this crystalline configuration, do some perturbation expansion or to do some treatment around the crystalline state to understand what kind of fluctuations you would have on the stress tensor for these configurations? It turns out you can exactly do that, and I'll describe some of our exact results here and then try to connect them with this field theoretic description of stress correlations. And it turns out surprisingly that at large length scales it matches exactly. So let me just go through that. What you can do is basically write down the force law that I was talking about, the harmonic force law, which happens to be a linear force law if the exponent was 2. So the force between particles exactly is basically this 1 minus Rij by Aij, but the thing to consider here is that this Rij hat, which is the vector pointing along the configuration, so particles I and j, leads to some non-linear force law. So it looks linear here, but if you were to write it down in the xy coordinates, which is the only democratic coordinate for all the particles, you would actually end up with Fijx and Fijy having this extremely non-linear looking function. And what you can do is do the same trick that you do in quantum mechanics. You start with the crystalline state and you create a perturbation expansion about the crystalline state, where this was the quench variable at every site. For example, this was in the case of the harmonic interactions, it was the size of every particle. You start with equal size particles, have a tuning parameter lambda, and just create perturbation expansion about the crystal. So you say as a response to the disorder, the positions of the particles change a little bit. This in turn leads to the changes in the interaction interparticle forces because of the, if you just go back, because you have a force law. So if the particle positions change, the forces will change accordingly. But now because of the change in the forces, you have to sort of expand this force law in the usual way that you would do, just create some Taylor expansion. Each of these coefficients, because they are drawn from the crystalline state, happen to be independent of the actual position. They are just translationally invariant coefficients, and you can sort of just write down the force balance equation at every site. I will not go into all the details, but what you can do is you can actually perform a systematic expansion of the displacement fields, systematic expansion of the forces, match the force law, that is impose force balance at every stage of the perturbation expansion, and I'm sorry if it went back. Match at every order of the perturbation expansion, and you can actually solve these equations. So you can solve the equations at every step, and you will get at first order in the forces in the perturbation expansion. You can solve for the force balance. Again, you can solve for the force balance second order, and so on at arbitrary high orders. So what have we done? We created a set of equations that will represent the change in the positions from the crystalline state as a response to the microscopic disorder in the configuration, but maintaining force balance at every stage. So once we do that, we can actually solve in terms of Green's functions. This is the last slide with a lot of equations. You basically write down what the change in the positions of the particles are in response to the microscopic disorder, which I can write in terms of some source fields, which basically these source fields contain the microscopic information about the quench disorder. And once you have that, you have the exact solution, because now you have enough equations to solve. You can actually write down all the displacement fields in terms of the microscopic quench disorder. This is different from the solution of linear elasticity, where you solved continuum elastic equations as a response to external forces. This is microscopic disorder inside in the configuration, solving for force balance. So once you do that, once you have the displacement fields, you can actually derive the stress tensor exactly, and you will be able to write down the stress tensor in terms of some microscopic variable, which is the quench disorder. Once you've done this, you can actually calculate the stress correlations, because every configuration of microscopic disorder leads to one stress field imposing force balance at every stage, and you can now calculate all the components of the stress tensor. So just to show you a proof of principle that this can be done, you can actually first calculate the displacement fields away from a single defect, and it matches exactly with simulations. You take one defect, or you increase the size of one particle, and you actually see that the simulations and theory matches exactly. You can also show that this, at large length scales, the predictions of continuum elasticity are recovered. You can actually get a 1/r dependence of the displacement field. Again, you can just put this back into the Cauchy-Navier equations that I showed right at the beginning, and you'll see that you get the predictions of linear elasticity. You can actually also go all the way to looking at nonlinear elasticity corrections. I will sort of skip over that, but you can show that linear elasticity predictions will tell you that superposition of solutions are allowed, but if you do the full perturbation expansion at every order, you will see, because you have nonlinear corrections, you can actually predict nonlinear corrections to elasticity, which I will not go into at this point, and you can go on and predict correlations between defects, interactions between defects, which exactly match because of this theory at near disorder. Okay, so now the question becomes, if you had a little bit of defects in the system, what happens to the stress fields? You can calculate the stress field produced by a single defect, and you can show that at large length scales, the source terms that I was talking about actually have this 1/r squared decay, which leads to anisotropic correlations, and you can actually get the full anisotropy only because of this the alpha beta components of the stress tensor. You can actually predict what the correlations are. This is exactly the prediction of continuum elasticity, because this is a non-disordered medium. But now we can take that prediction of the stress tensor because coming due to the disorder and now compute the correlations exactly, because if I want to compute the correlations in Fourier space between the components of stress tensor, I had written everything in terms of the source field. So all I have to do is calculate these source field terms, and because I know the correlations between the microscopic disorder, I get the answer for the stress tensor correlations. And it just looks a little complicated, but everything can be written in terms of the geometry, the interactions, and the angular dependence of these interactions, and we can actually find the exact correlations, and I will show you some answers based on this. Okay, so here's what we find, right? So if I was to look at the correlations in the stress tensor for near crystalline packings, we actually see that if I look at the correlations between the XX components, so sigma XX correlations in Fourier space, this is what I mean by the pinch point singularities. You see, in Q, this is QX and QY, if you come along this direction, you have some correlations. If you come along this direction, you have zero correlation. Come along this direction, you have a positive correlation. And all of them meet at this point Q equal to 0, which is telling you that the Q equal to 0 point is singular, and the approach in different directions has different limits. That is this sine to the 4 theta that I had shown you right at the beginning. So this is true in both the harmonic interactions as well as the Leonard-Jones interactions. In both cases, you can actually do the same perturbation expansion and get exact results. And this is the integrated correlations. We're just basically integrating the correlations in theta. So this is the theta in Q space, and you can see this is the sine to the 4 theta, and it matches exactly. Similarly, you have XX and XY correlations, which have the sine square theta, cos square theta dependence. And this is the XXYY correlations. So I'm not going to go into this, but we see some small deviations because of the crystalline nature, which we are still investigating. But on the whole, these look very similar to the correlations you would derive from the field theory. So then you can match them at all Q, not just at small q. This is just a proof of principle that if you looked at the correlation function of the stresses in the entire QX, QY range, the theory and the numerics for the near crystalline packings match exactly. So then the question becomes, what happens if I look at fully disordered packings, not just near crystalline, not small deviations from the crystal? What we could do, so this is work we recently did, where we looked at all possible boundary conditions, where you take commensurate a box where you can create a triangular lattice. You can look at an incommensurate box where the triangular lattice is not it does not yield a crystal. You can take the disorder all the way from very, very small disorder, which is this eta equal to 0.005, which is basically a polycrystal, and create a disordered configuration all the way to a fully amorphous configuration, and measure the stress tensor and the stress correlations in this system. So that is what we did. So this is what we saw at large length scale. So we basically looked at all of these configurations at all different eta. This is very, very far from a crystalline configuration. It's actually a completely amorphous state. And if you look at the orientation correlations, you see a completely amorphous state. And we looked at all of these correlations, and they all fall on top of each other. If you look at the radially averaged correlation function in Fourier space, this is for all of them. At all eta, they basically fall on top of each other. And here is the point that I was sort of burying under the rug. There is a small difference here in the angles depending on whether you're in the crystal or not in the crystal, but that is the only small difference that we are sort of investigating at this point. But at very large length scales, because this is the small q behavior integrating around small q, you get universal correlations. So this large length scale behavior actually you can do in multiple ways. You can actually divide by the pressure correlations, and it turns out that if you divide by the pressure correlations, all the data collapses onto one master curve, regardless of what packing fraction you started with, regardless of what disorder you started with, because depending on the pressure, there would be, if there was large initial pressure in the configuration, then there would be large stress fluctuations. So the magnitude of the stress fluctuations exactly can be normalized by the pressure fluctuations, and you see this master curve. And here this is sort of the main result of our work, where we are showing all the components of the stress tensor can be predicted exactly. And let me just go here. So you have some small dependence on the pre-stress, which can again be incorporated into the pressure fluctuations for both the models. The pressure in the Leonard-Jones model and the harmonic model, you actually get they depend on the pressure, but if you scale it by the pressure square, you get universal correlations. So then the last point I would like to make is that you can look at the transitions that happen. For example, as I mentioned, if you start with a crystalline state, you add some disorder, you will actually have a disorder-induced transition. So in the short-range model, you have a very well-defined amorphization transition. In the long-range model as well, you have a very well-defined amorphization transition, which you can measure through orientational correlations as well as the fluctuations in the orientation correlations. And across this transition, it would be very interesting to see what really happens. How come the stress tensor correlations are so universal? And so this is my last slide. We see this very interesting behavior. In the crystal, if you look at, this is just XX correlations, the sigma XX correlations. If you look at this is eta equal to 0.3, so it's not near crystalline. It is quite far away from crystals in the sense that it has large fluctuations in the stress tensor, but because you're below the transition, so let me just go one slide back, the transition happens around 0.4, so this is at eta equal to 0.3, you actually see a Brillouin zone. Brillouin zone is periodicity in Fourier space. So you see these correlations that I was showing. These are the pinch point correlations I was talking about at q equal to 0. But you see a very interesting Brillouin zone appearing here. But as you go past the transition, you see this loss of Brillouin zone. So the short range, the long length scale physics, which is buried in this q going to 0 limit, really remains unchanged, as I was saying. So there is a universality at q going to 0, but the short length scale physics really seems to show you that the Brillouin zone gets lost, and this correlation function seems to give you a very direct way to measure the transition between amorphous and crystalline. This is an intriguing direction we hope to pursue in the future, but with that I'd sort of flash my conclusion in summary, and I'd be happy to take questions.
So yeah, questions for Kabir?
Yes.
Yeah.
Hey, so in the Leonard-Jones potential that you had used, right?
Yeah.
And you said you used a cutoff for Rij divided by...
Aij divided by 2.
Yeah, right?
Less than 2.5.
So that's that makes sense if you if the particle that you're considering is very small, right? But if the kind of
so this is the representation of how far the interaction goes.
Correct.
So it goes up to the third shell.
Correct.
So
But in a classical sense, the Leonard-Jones is typically used for molecular systems where the cutoff is much smaller, right?
no, this is usually the cutoff. 2.5 is what, for example, the glass models are sort of they tune it, but 2.5 is the usual cutoff for glassy systems as well.
Okay.
So we used exactly what is there in the literature. In fact, even this quench disorder parameter, we did not invent it. It's sort of used very frequently to study this amorphization transition in the Leonard-Jones, but it goes all the way till here.
Sure.
But you're right, like we don't want it to go too long. The reason is because otherwise you cannot do computational studies. Then you'll have to keep track of all the neighbors. So 2.5 is the usual cutoff distance. But yeah, you can tune that a little bit. Yeah. Thanks a lot. Yeah.
This follow-up of Ganga's question, I mean, I still don't understand the directionality that comes in your system. Is there an intrinsic anisotropy, or your defect by definition picks up some direction and that's where you see the anisotropy?
No, so the anisotropy comes in from the fact that you are looking at, so I'm looking at XX correlation. So this already breaks the spatial anisotropy. So the sine to the 4 theta is coming because I'm looking at along a particular direction. But I can do a transformation of coordinates and actually transform this into this. And I would get sine to the 4 theta goes to the cos to the 4 theta, yeah.
So therefore, the elasticity that you have in the system is still going to be isotropic.
Yes.
And if you were to write it in a tensorial notation, then you wouldn't have this confusion. Is that correct?
Absolutely. In fact, this, what I have written down here, is the Lamé coefficients for isotropic elasticity. If I was to look at, for example, orthotropic elasticity or some locally broken symmetry elasticity, I would get off-diagonal components here. But this is isotropic elasticity. But that's a very good question. So if I added these terms, I would get deviations from this behavior. This is the isotropic case. Yeah, this is a very good question. Yeah, thanks.
When you were doing all the derivation, you said that you could get nonlinear contributions, but in the derivation I got the impression that all the assumptions are linear because you expand in small variations and then you use linear elasticity to couple displacement to stress. So I don't know in which sense you talk about nonlinear.
Thanks a lot. That's a great question. I went quickly over that. So let me go two steps back. So the linearized assumptions was for the derivation of continuum elasticity. This is exactly linear. So this is not what I'm using to calculate the nonlinear corrections. So let me go to the perturbation expansion that I was describing. As I said, I can take an expansion to all orders. So I go, if I calculate the forces linearized in the displacement fields, this would represent, for example, the Lamé coefficients up to this order, because it only depends on xij, the relative displacement between particles. But in the force law, I can go to any order that I like. So this, for example, here would involve xij. This would give me linear correction, nonlinear corrections. So when I do this, and let me just go one more step back. I didn't show all the details. I can actually calculate this linear coefficient, nonlinear coefficient, go to all arbitrary orders, and when I impose force balance, this would give me the linear elasticity. So I say I have some displacement fields which are related to my microscopic disorder, and I can solve this. Then when I impose force balance at every order, I can actually hierarchically solve these equations. I didn't show that. The second order equations actually involve, the second order solutions will involve the first order fields as a source term. So you can actually do that, and just to prove that point, let me go here. Yeah, so what you can do is, using this hierarchical scheme, because I'm solving it order by order, linear order, second order, third order, what you can show is that if you place one defect at some, let's say the origin, you have the first order solution, second order solution, third order solution, because you have corrections at every order, and you place another defect at some distance delta, you have the same corrections. Now you place both defects together in the system, so you can have, because of both defects at 0 and delta, you get first order, second order, third order. Now linear order solutions would have superposition, that is two defects in the system would have a linear superposition of the 0 and the defect at 0 and the defect at delta. This is what continuum elasticity or linear elasticity would predict. But what you can do is calculate just the difference, put two defects together and subtract the individual displacement fields of each of them, and then get a prediction from here. So the left hand side, actually this is a experimentally testable prediction. You create two defects and calculate the displacement field, subtract the individual displacement fields, whatever is remaining would be corrections to linear elasticity. And in fact, the theory that I was describing, the nonlinear theory all the way to second order, gives you the exact values. These are tiny, because in the log scale these are actually very small, but you can actually predict it exactly. So that's, so when I'm calculating stress correlations, I'm only doing linearized. But in principle, you can go higher. So let me just go here. When I'm calculating this is absolutely, as you pointed out, this is just linearized. But you can in principle go to higher order. Yeah. Thanks a lot for that question.
Thanks, Kabir. Let's all thank the speaker once again.